video, I will be talking about how bones grow and remodel, as well as talking about different types of bone fractures and homeostatic imbalances as it relates to bone. So, bone is going to develop via one of two different ways. You have either intramembranous ossification. In this type of bone formation, the bone develops directly from mesenchyme sheets. This happens in the flat bones of the face, most cranial bones, and the clavicles. Here, the secreted osteoid so this is the osteoid from these um, osteoblasts are going to eventually trap the bone, which are going to become then osteocytes. The trabeculae matrix and the periosteum are going to form, and then the spongy cavity is going to be infiltrated with blood vessels and fill with the red bone marrow. The other type of bone formation is the endochondral ossification. This is when the cartilage takes the form of future bone. So the mesenchymal cells are going to develop into chondrocytes first. As the matrix calcifies, nutrients are no longer going to be able to reach it. So we can see calcification starting to take place. Thus, you're going to have blood vessels invade this space that helps to give the nutrients into these spaces with them. It carries osteogenic cells within it. And as this happens, the chondrocytes continue to grow at the future epiphyses, increasing bone growth. After birth, the head of the bone or the epiphysis is going to be infiltrated. So this down here is a primary ossification center. This is going to be a secondary ossification center where the bone forms. And ultimately, cartilage is just going to remain here at the epiphyseal plate and at the articular surface where it will articulate with another bone. So this is going to be the type of bone growth that helps by replacing the hyaline cartilage that's placed there before, and this is going to be what most bone formation is going to occur as. Now, as you may assume, because you have a growth plate, the bone growth is going to continue. So the epiphyseal plate is an area of growth in a long bone that happens after birth. It's going to consist of a layer of hyaline cartilage where ossification is occurring in these immature bones prior to adolescence. So if we look at the different zones, we have the reserve zone. This is the zone that's closest to the epiphyseal end and will contain the chondrocytes within a matrix. You have a proliferative zone. This is going to consist of stacks of chondrocytes. New chondrocytes will be made here via mitosis. You have the zone of maturation and hypertrophy. So here the chondrocytes will accumulate lipids, glycogen, and alkaline phosphatase. And this is going to be the site where the matrix is starting to calcify. The zone of calcified matrix is next. This is where the chondrocytes will begin to die and deteriorate. And then you have the longitudinal bone growth that ends at the zone of ossification where the new bone is growing. So this longitudinal bone growth is going to completely end when the epiphyses and diaphyses fuse. Typically this happens about at 18 to 21 years of age, with it typically happening in females slightly before males. Longitudinal bone growth does stop, but you can still have growth in width by appositional growth. So the osteoblasts in the periosteum are going to secrete the matrix, while the osteoclasts in the endosteal surface are going to remove. So you have the epiphyseal plate lines that you see there, appositional growth, growing wider. This is going to be a balance between the actions of osteoblast and osteoclast. Generally speaking, more building than breaking down is typical. This results in a thicker, stronger bone, but keeps them from getting too heavy. So bone remodeling is a dynamic and active process that is going to continuously go through small scale architectural changing. So your skeleton is going to essentially be replaced entirely every about 10 years. The remodeling process is going to replace about 5 to 10% of the skeleton annually. Not all bone is equal, so spongy bone will be replaced every 3 to 4 years, while compact bone is more slowly, about every 10 years. Its remodeling is going to be essential for bone health. Long-standing bone accumulates crystallized calcium salts that results in more brittle bone, making the bones more prone to fracture. So how this works, you have osteoclasts that are going to cling tightly to the bone, sealing off the area that will be destroyed. The dissolved matrix is going to be transported through the osteoclast, enter the interstitial fluid, and then go into the bone. The osteoblasts then are going to replace the osteoclasts. So the osteoclasts will go through apoptosis, osteoblasts come in, they lay down the new matrix, and will start the formation of osteoid seam, which is unmineralized. All right. So calcium is essential for this process, but it is also essential for maintaining the resting membrane potential of all cells. So normal blood calcium levels are required for proper nerve firing and effective muscle contraction. If you look at the amount of calcium in the human body, you have about 1,200 to 1,400 grams. Most of this is stored in bone minerals, with about 0.9% being found inside cells and less than 0.1% being extracellular fluid. However, because it is so essential for resting membrane potential, bone is going to serve more as a calcium reservoir, allowing for withdrawal or deposit of the bone depending on what it needs. And hormonal control is going to help keep blood calcium levels within a tight range. So homeostatic levels of calcium in the blood is what is really being monitored. Hormone control is going to be more concerned with the blood in the calcium versus the blood in the bone. As mentioned, constant levels, which is about 9 to 11 milligrams per deciliter. The bone will be resorbed from the bone, or the calcium will be resorbed from the bone, bringing it into the blood so that it can go into calcium and go into muscle and nerve cells to help maintain their resting membrane potential, as well as the resting membrane potential of other cells, which is more constant. And then the calcium can then leave there, go back into the blood, and be resorbed into the bone when there is too much levels of it. Calcium goes down. So this signaling is going to be moderated by the parathyroid hormone. So the parathyroid gland is what is secreting this. Parathyroid hormone, which is abbreviated commonly as PTH, is going to sense, or the parathyroid gland is going to sense the low levels of calcium, going to increase the secretion of parathyroid hormone. This then is going to increase the rank L activity that stimulates the formation and activity of the osteoclast. So this is increasing the osteoclast activity. And then you have calcium going back into the blood, raising the levels. In the opposite effect of this, you do have sex hormones that will, like osteoprogesterone, that are going to inhibit rank L and stop the osteoclast activity from happening. Calcitonin release from thyroid is done in response to elevated blood calcium, but the function on the regulation of calcium is essentially negligible. So sex hormones increase the synthesis of rank L's antagonists, and that's how it inhibits the osteoclast activity. Vitamin D and glucocorticoids, on the other hand, are going to indirectly stimulate osteoclast activity by increasing the activity of rank L. All right, control of parathyroid hormones, again, is going to act to preserve blood calcium concentrations and is not concerned with the skeleton's overall strength or well-being. So control of parathyroid hormone controls both whether and when remodeling will happen. So if blood calcium levels go too high, you're no longer going to stimulate the parathyroid gland to secrete parathyroid hormone. Parathyroid hormone goes down. You're no longer going to stimulate the osteoclast activity, and you're going to basically be putting down more calcium than you are resorbing, and so that overall is going to decrease the blood calcium levels because now more of it's sticking around later. So whether and when it happens is stimulated by parathyroid hormone. Where remodeling happens is related to where stress is happening on the bone. So the rule that governs this is known as Wolff laws. So it basically states that bone is going to grow or remodel in response to where the demands on bones are being put. So you can see over here, you have the load on the femur head. It's going to be compressing the bone on the more medial end of it, or more medial, and then on the lateral side of it, it is going to be compressing or taking the bone off. So it's going to have stretching that occur. This means that the thickest portion of the bone is going to be along the diaphysis midway, where the bending stress is the greatest. Minimal stress is going to occur at the bone center. That allows for the hollow structure. A few things that are explained by Wolff's Law are how the dominant, sorry, the, have more diagrams coming up here. So here there's more bone building happening along where you have greater tension and compression, and less bone building, more breakdown where you have it along. So some things that are explained by Wolff's Law includes handedness. You'll notice that dominant arm bones tend to be thicker due to more frequent use. Curved bones are going to be thickest where they are most likely to buckle. Trabeculae and the spongy bone align along lines of compression. You have large bony projections form where strong muscles attach, especially in weightlifters. Unstressed bones, such as those that happen in fetuses or bedridden individuals, tend to be more featureless or atrophied along this as well. All right, so what I want to emphasize here is what I said at the start, is that the response to mechanical stress influences where the remodeling occurs in the bone. All right, fractures represent one form of a homeostatic imbalance when it comes to bone. So fractures may be classified the position of the fractured ends. You can have non-displaced fractures where the bone end retain their normal position, or you can have displaced fractures where the bone ends are out of normal alignment. It can also be classified by the completeness of the break. So if it breaks through the bone completely, that will define it as a complete fracture, where if it is not being broken completely through, it's an incomplete fracture. So over here on the right, this represents a displaced fracture, while this is a non-displaced one because the bone is out of alignment. Here in this middle picture, we have a complete fracture on the left because it goes completely through the bone, while on the right we have a incomplete fracture since it only goes through partially. And then the final way you can classify a fracture is based on whether it penetrates the skin. If it's going through the skin, like we see here, then we call it an open or a compound fracture. If it's not, then we say that it is a closed or simple fracture. There are other ways of classifying it, or fractures as well. So one, and that's basically based on how they occur and what bones they are breaking. So one example is a comminuted fracture. So this is classified based on the number of fractures. So if you have more than two parts, we say it's comminuted. Compression fractures are going to be when you have crushed bone. This is going to be common in older adults, which have more brittle bones. They generally are going to have more porous bones than when they're subjected to trauma. Those bones are more likely to break. The next type we have is a spiral fracture. So this is going to be a ragged break that's due to excessive twisting forces. This is a common types of sports fracture that can occur because you're twisting on the bone during these actions. In an epiphyseal fracture, the epiphyses are going to be separated from the diaphyses along the epiphyseal plate. This occurs because the epiphyseal plate has cartilage cells that are dying, and the calcification of the matrix makes it more prone. So this has to happen before the growth plate has fused. Um, a depressed fracture is when the broken bone portion is pressed inward. This is going to be common in a skull since there's not much direction for the bone to go. And then the incomplete fracture that I talked about is known as a green stick fracture. This is going to be common in children who have relative elasticity in their bones. So this allows part of the bone to break while the rest of it stretches. Think of taking a very green part of a plant and twisting it. When that happens, or bending it, when that happens, you'll notice that part of it will break, but the rest of it will stretch, and that's essentially what's happening in these green stick fractures. So fractures are going to require bone healing to occur. This is going to occur in several steps. So it's going to begin with the formation of a hematoma. The hematoma results from the hemorrhage blood around the bone, and this happens because you have damaged blood vessels that come here. Bone cells that are deprived of nutrients tend to die, and then this tends to be painful, swollen, and an inflamed area. This inflammation is going to trigger recruitment of different things there to help heal this site. So in this, the fibrocartilaginous cartilage is going to form. A callus means hard skin. So basically new blood vessels are coming into the clot, and you have fibroblasts and chondroblasts invading the fracture site. They come from the periosteum and the endosteum. The fibroblasts are going to produce collagen fibers that span the break, while the chondrocytes are going to secrete a cartilaginous matrix that bulges externally and later calcifies. The mass of repair tissue is called a soft callus since it's made up of cartilage and is relatively soft. The next step is going to be when a bony callus forms. The bony callus is going to be made up of more bone because the osteoblasts are going to begin forming around the spongy bone, or forming around the break with spongy bone. The trabecula span the width of the callus and unite the two fragments of broken bone. The fibrocartilaginous callus or soft callus is going to be replaced by an immature bone. Thus, we have our bony or hard callus being formed. And then the final step is going to consist of remodeling. So bone remodeling is going to occur. You're basically going to get rid of some of the excess material on the exterior and interior, and compact bone is going to be laid down to reconstruct the shaft walls. You'll notice that after the growth has occurred, it won't necessarily be the same structure as it was before. Typically, you have thicker walls being found where you had this bone growth occur to help strengthen the bone. Some other homeostatic imbalances include osteopenia. This is a condition of low bone mineral density. It may not actually cause symptoms, but it puts you at a higher risk of osteoporosis. This condition is when you have bone resorption outpacing the deposition of bone, and so this leads to low bone mass. In addition to that, you have microarchitectural deterioration of bone tissue that increases the risk of fracture. These are diagnosed with DEXA scans. If you have it below negative 2.5, that generally indicates osteoporosis is beginning to occur. These lead to an increased risk of fractures overall. Risk factors for osteoporosis includes a history of osteopenia, decreased sex hormones, or insufficient bone stress can lead to increased risk of osteoporosis. That's why it's important to do body weight and weight bearing exercises to help strengthen your bones. A diet that's poor in calcium, vitamin D, or protein, basically the parts of your body that make up bone, can lead to weakened bones. Smoking and genetic factors also play a role. Diabetes, hyperthyroidism, other hormone related conditions can mess with your handling of bone resorption and deposition. And then certain drugs like alcohol can also increase your risk of osteoporosis. Another form of a homeostatic balance is osteomalacia. So this is when the bones get poorly mineralized. Generally, you have enough calcium in these cases, and well, I'm thinking of rickets specifically, but you have low levels of vitamin D. The main symptom of osteomalacia is pain with weight, but it can also cause other problems as well. Rickets is analogous to osteomalacia, except it happens in children and can result in deformities since the legs are still growing. So you can have bowed legs, deformities of the pelvis, skull, and rib cage. As I mentioned before, insufficient calcium can contribute to this, but a bigger risk factor is vitamin D. All right, so this concludes our discussions of bones. We will be looking in the next chapter at our joints.